The trough in the figure is to be made to the dimensions shown. Only the angle theta can be varied. What value of theta will maximize the trough's volume? Let's begin by looking at the face of this figure. The face is a trapezoid, and we are told that this dimension is 1 foot, and this dimension is 1 foot. And we are told that this angle is theta. And we see that we have formed a right angle that would be matched on this side and then form right triangles. So we could break the volume of this thing up into 3 different pieces. We'd have the rectangular piece and then extend it out for 25 feet. And we could find that volume very easily. And that volume would be dependent on the length, 25 feet, the width at the bottom, 1 foot, and then the height, which we don't have a value for. So maybe we'll call that h. Then we'd have the parts that are formed by the triangles on the outside. And we have 2 of those. And each of those volumes we can see would be calculated by the area of that triangle times the length of the trough. So let's think about the area of that triangle. So this triangle, we are told, has a hypotenuse of 1. We have an angle theta, and we have labeled this side h. Now the area of that triangle would be 1/2 the base times the height. Using the Pythagorean theorem, this side, the horizontal side, would be the square root of the square of the hypotenuse, so 1 minus the square of the other side, so h squared. So this area would be 1/2 the base, square root of 1 minus h squared, times the height, h. So the total volume would be the volume of each of those triangular sections. So that would be 1/2 times the square root of 1 minus h squared times h times 25 plus 1/2 times the square root of 1 minus h squared times h times 25 plus, and then the volume of the rectangular section, which would be the base, 1, times the height, h, times the depth, 25. Now we could simplify this then. Volume equals, this last term we might write first, that would be 25h. Adding the other 2 terms together, the 1/2 would go away. And rearranging the factors a little bit, we would have 25h times the square root of 1 minus h squared. Now, we have volume in terms of height, but we were supposed to find this volume in terms of the angle theta, because we were told that is the only thing that is variable. So let's work on that for a second. Looking at this triangle, we can see that the sine of theta would be the opposite, h, over the hypotenuse, 1. So the sine of theta would be equal to h. And I could substitute each of the h's in my expression for the volume with the sine of theta. So we would have 25 sine theta plus 25 sine theta times the square root of 1 minus the sine squared of theta. But 1 minus the sine squared of theta is the cosine square. So this would be then the same as 25 sine theta plus 25 sine theta times the square root of the cosine of theta. But the square root of the square of the cosine of theta would just be the cosine of theta. So our volume then just becomes 25 sine theta plus 25 sine theta times the cosine of theta. So we have a function v equals 25 sine theta plus 25 sine theta cosine theta, where we have the volume expressed as a function of the angle. We could find the first derivative then and set it equal to 0 to find where this function is maximum. So we will find dv d theta. So that will be 25 cosine theta plus 25, and now we'll use the product rule. Sine of theta times the derivative of the cosine theta, which will be the opposite of the sine of theta, plus the cosine of theta times the derivative of the sine of theta, which would be the cosine of theta. So dv d theta would be equal to 25 cosine theta plus 25 times negative sine square theta plus cosine square theta. We can convert the sine square of theta into 1 minus the cosine square of theta. So if we do, we would have dv d theta equal to 25 cosine theta plus 25 times the opposite of 1 minus the cosine square of theta plus the cosine square of theta. And simplifying this, we have dv d theta equal to 25 cosine theta plus 25 times negative 1 plus the cosine square of theta plus the cosine square of theta, which we can then write as dv d theta equal to 25 cosine theta minus 25 plus 50 cosine square theta. We have a common factor of 25, so we can write that as dv d theta, and then factor out a 25 and rewrite these in an order that we might find more convenient to work with. So we'll put the cosine square first, so 2 cosine square plus cosine theta minus 1. Now we should set that equal to 0. So we would have 25 times 2 cosine square theta plus cosine theta minus 1 equal to 0. But we could factor 2 cosine square theta plus cosine theta minus 1 into 25 times 2 cosine theta minus 1 times cosine theta plus 1, and then set that equal to 0. So really what we're interested in then is when is 2 cosine theta minus 1 equal to 0, or cosine theta equal to negative 1. Now let's talk about first when the cosine of theta is equal to negative 1. If we look at the unit circle, the cosine of theta is negative 1 at pi. If this angle theta is pi, then it would be obtuse, not acute. And in order for this trough to have this shape, theta is going to have to be an acute angle. So let's look at when 2 cosine theta minus 1 is equal to 0. And we could add 1 to both sides and then divide both sides by 2, and we have cosine theta equal to 1/2. That occurs when theta is pi over 3. So the volume of our trough is maximized when theta is equal to pi over 3.